We continue our discussion on interacting species. This is part 2 of 3. We are in the process of computing an interior steady state or an equilibrium point that lies in interior of the first quadrant in the phase plane. So we had reduced our calculation to the equation of a line. In fact, we had two lines, both of which have negative slope, and both of these lines have a positive intercept with the vertical axis. Let's take a look at this is a graphical representation of a line that has this equation. Clearly the intercept with the vertical axis is at lambda over b, and is also another thing we point in this sketch is that the intercept with the horizontal axis happens at lambda over a. Now on the right hand side we have the other line, and it's easy to see that the intercept with the vertical axis happens at mu over d, and it crosses the x-axis at mu over b. So what we really like to do is to put both of these lines in the same figure, okay? And this is what we do next. There are four possibilities as to how this figure may look like. The information we have at hand is that both lines have negative slope, right? Minus a over b, minus beta over d, and that they both have positive intercept with the vertical axis. So this is the figure for the first case. Here we describe the cases with these inequalities. We note that the first inequality refers to these points on the x-axis. So we have mu over beta is smaller than lambda over a. The second inequality refers to conditions as they happen on the vertical axis. Mu over d is less than lambda over b. If this is the case, you can see that there is no intersection in the first quadrant. In fact, these two lines would be intersecting at somewhere on the fourth quadrant. Let's take a look at the second case. The second case is when lambda over a is less than mu over beta. Together with lambda over b, here this intercept is below mu over d. In this case, the intersection between these two lines doesn't happen on the first quadrant. It's suggested here by the sketch that these two lines will intersect somewhere on the second quadrant. Case number 3. In this case, lambda over a is smaller than mu over beta, and mu over d is less than lambda over b. In this case, these lines intersect on the first quadrant, and this intersection, this point of intersection, will define or give rise to a steady state or an equilibrium point of our system. There is a fourth case when mu over beta is smaller than lambda over a, and when lambda over b is less than mu over d. This also gives rise to another point on the first quadrant. So now that we have identified possible scenarios, we're gonna solve the system numerically, and we're gonna illustrate some of these cases. In summary, we had previously summarized. We had points lying on the boundary of the first quadrant. Here is one of those points, lambda over a comma 0. Then we have 0, 0. This first point is what we would label as extinction of species number 2. Here the second species goes to 0. Basically the species number 1 outruns species number 2. The trivial steady state is when both species go extinct, and then this other point is the extinction of species number one, meaning that basically species number two drives species number one to extinction. Okay, now the new point is this point that lies that may exist under some conditions and lies in the interior. When that happens, that point has these coordinates. The first coordinate and the second coordinate are expressed here. These are the four equilibrium points or steady states of the system. Now we're going to revisit some illustrations as to see when and how some of these points are stable. We'll see that this total extinction equilibrium point is never stable. Here is an illustration for case number one, and this is the scenario in which species number two goes extinct. Here is that point. What we did was to set some values for the parameters, and this is a phase plot. So we have y of t versus x of t, and we have three curves. Each of them with a different set of initial conditions. All these simulations are calculated using the package the R package LSOTA. So here we have a curve that starts at x0 equals 1, y0 equals 1, and this curve converges to this point. Then we set initial conditions 10 and 40, and this curve quickly converges here, and similarly for the numerical solution obtained using initial condition 16, 20. Okay, you can see that this point lambda or a comma 0, given the numerical the parameter values used here, that point is basically 20, 0. Now for case number two, which is the scenario in which species one goes extinct. This is the equilibrium point 0, comma mu over d. We're testing numerical solutions with three different initial conditions. We initialize at 1, 1, initialize at 35, 1. This would be x at 0 is 35, y at 0 is 1, and you can see how these curves are quickly converging to the point 0, mu over d. This is the third initial condition. In this case, mu over d, we chose parameters so that mu over d is 50. So this is converging to the point 0, 50. The next case, case number 3, is what we call coexistence. In the previous two cases, there was an exclusion. Basically, one species drove the other species to extinction. In this case, both species would maintain levels. They would stabilize at equilibrium levels that are positive. We depict that equilibrium point in the phase plane with a circle here. Here is the expression we had presented before. In this case, there are three solutions. We chose parameter values and tested different values for initial conditions. Here's one curve, starts at 1, 1, and quickly converges to this equilibrium point. Then we had 15, 5 and 10, 50, and the three solutions converge to that equilibrium point that is called coexistence. And the last case is a case that allows for stability of either extinction of species 2 or extinction of species 1. So both of these steady states are stable, therefore the name here bistability, meaning that there is stability of both. And here is the equilibrium point in the interior. In this case, this equilibrium point is unstable, and the sense that is unstable can be explained that in the sense that stable points are limits, right? The solutions converge to the point that the equilibrium point we call stable. When a point is unstable, so the stable point is attracting solutions, and the stability has that sense of converging to it, right? There is like a magnet, there is an attraction. On the other hand, when a point is unstable, then there is a repulsion. Is the point is repelling trajectories. And so you can see that there are four curves here. There are four initial conditions tested. These solutions starting at 110 converge to 0 mu over d, and these at 1240 also converge to that point. But when we look at the solution with initial condition 1, 1, then that converges to the other point. And with these initial conditions 45, 60, it also converges to the other point. So this, in this case, the interior equilibrium point is repelling, is unstable, and solutions are moving away from this point. They're moving away towards either extinction of species 1 or extinction of species 2. Okay, so this allows for what is called bistability. This was a scenario in which parameter values were set, and for the calculation of these four curves, the parameter values are the same. The only thing that changed from one scenario to the next was the values used for the initial conditions. And this concludes our discussion of interacting species part 2.